This is the very first problem.
Yeah, that's what
Yes.
Yeah.
Yes.
It's like the Catalan numbers can also like show like when something crosses. Like
Yes,
instead of you doing a problem with parentheses, we can do
Yes.
a problem on a graph, a 2D graph.
Yes. So let's go back to the Catalan numbers.
Something of like there was like like you usually phrase it as like the politician who can't stand to ever like during an election to be ever losing or something.
Yeah, that's one way to put it. Another way to put it is that you're walking in Manhattan and you are going from here to there, but you always need to stay on one side of the line. You always need to stay above the line. So for example, here's one way to do it. Like so. Right? And then you can ask the same, this is actually the exact same question as Catalan numbers, to say the number of paths never go below the line. So this is going to actually be a faster proof than the previous one that I showed. I just wanted to show the previous one because it gives a tour of some other concepts in combinatorics. So for this one, it's actually kind of hard to do the number of paths that never go below the line. However, we could take the total number of paths from A to B and subtract the ones that do go below the line. Okay? So since the number of paths from A to B, I'm referring to the paths that are always going up and to the right. Since this is equal to 2n choose n, it suffices to find the number of paths that never go below the line. Okay? So how do you go about doing this? Sorry, wait. That do go below the line. Let me change that. That do go below the line. So the ones that cross the line. And what I wanted to illustrate with the second part of the talk, which is shorter, is this thing called the reflection principle. We're going to do something where we flip. Reflection. So suppose we have a path that goes below the line. To go below the line, since we're taking integer steps, it means you actually touch the line that's one below it. Okay? So if you're actually going to go below the line, here's your line. And there's something that's exactly one offset below. Like from here and here, like this. So go below the line is exactly the same as you're going to touch the dotted line. So let's look at a sample such path. Here's one. It kind of goes up a bit, maybe halfway. It goes right across, it touches this thing, and it just keeps going across, and then it goes all the way up. Here's a simple one. Okay? We want to count all the ones that cross this line, or touch this line over here. I'm saying there's this reflection idea. So what you can do is for each one of these, let's consider reflecting it the moment it touches the line. Okay? So let's associate this path with a different picture. And the other picture looks like this. Actually, it doesn't look like this because there's not enough space. What I'm going to do instead is I'm going to draw the other picture on top of it because it's easier to do a reflection in place. So what I'm saying here is reflect across the dotted line after moment of first hit. Okay? What would that look like? Can someone tell me what I do? Like it would be where the other one continues to go in and touches this line. But at that point, it does the opposite. So what I mean is now it goes up, and then it goes across. It stops here. Does this make sense? I could count that instead. This dotted line, this one instead that goes across and ends at B prime. We actually want to do some sort of a bijection. What we want to show is that for every one of the paths that touches this dotted line, there is exactly one path that kind of is reflected across it and goes somewhere else. Well, there's something nice about this. Let's do another example. it always goes to the same somewhere else. That's a very important initial observation. Because if I have anything else, well, this is the solid line, this is the dotted line, even if it's doing something else, like maybe going up a bit, maybe even just touches this one, and then maybe just jumps all the way to the top and goes to your point B. If you do that reflection across the dotted line, then it's going to land at this point B prime. And it's the same B prime. Is that clear? This is a really nice observation. That it's okay. That
Literally my alarm this morning.
all right. That the reflection always fits the same point ends at the same point B prime. Okay. So let's try to take a closer look at all of these. We just showed that every one of these original paths, you can do a reflection, and you can get something that ends at B prime. Let me write that down. For each invalid path from A to B, you can get a path from A to B prime. This is not yet anything like a bijection. Well, it is something like a bijection, but we're not done yet. What else do we need to show?
That the number of paths from one is the same as
Yeah, we are ultimately, our goal is to show that the number of invalid paths here is exactly equal to the number of paths there. If you want to show exactly, you need to establish a bijection. So right now we just provided one way to go from these to those. What else do I need?
one that goes from
The other way. Does that make sense? To show that I have a bijection, it's enough to show that there's a function that goes from here. Anything in here, I get something from there. And the other one, where anything in here goes to there, and they are inverses of each other. Does that make sense? So what's the other way? What's the inverse?
There's another reflection.
There's some other reflection. What you're saying is that we need to show that for every path that goes from A up to this other B prime, it comes from the reflection of some invalid path from A to B. But which one would that be? You unreflected, right? What you,
Reflections are,
well, reflected is the same as unreflected because that's the order is 2. That's great. So what you're saying is suppose that somebody gave you a path from this A to this exact B prime, and somebody gave you some path. And maybe it's doing this. Okay? Then what you do is you unreflect it across this dotted line at the moment where it first touches it. Okay? So you find this first moment of touch, and then you reflect after. So it actually comes from this one. Does that make sense? There's one final piece of this that you need though, which is how do you know there's even anything to reflect? How do you know there's a first moment of touch? What if you can't reflect?
Because A and B are on opposite sides of the line.
Because of the intermediate value theorem, right? So this is actually what you, well, intermediate value theorem is not quite right, because these are taking integer steps. A funny comment is I was having lunch with some of the CMU students, and one of them commented they were trying to catch a bus using the intermediate value theorem with the idea that they were going from there to there, and there was a bus coming along the same line. So the idea, of course, was that you just walk until you see the bus, and then you just wait at the next stop, right? But unfortunately, I guess, in Pittsburgh, the traffic is better than New York. And unfortunately, intermediate value theorem doesn't work on Z. so
It doesn't work. I'm confused.
what I'm trying to say is that they got to one stop, didn't see the bus, started walking, and halfway between them and the next stop, the bus went by.
Yeah. Yeah, because the stops are,
Because the stops are on Z, but the bus is not, right? That's actually relevant to this. You do have to note that since this is on an integer lattice, and you're taking steps that are one up and one across, you will actually hit this point. That's an important note because you might be interested in generalizations to this question where you take 2 steps up and 1 to the right and weird things like that. And now if you're taking steps that might potentially jump over, you can't use this intermediate value property. Okay, that's all I wanted to comment. But okay, reflect after. And you're sure that it hits this dotted line by, I'm just going to call it the intermediate value property. Okay, that's great. So now we have just established that the number of these paths is the same, number of invalid AV paths is the same as the number of AV prime paths. What's that then? How many from A to B prime? Well, what is that? That's not a square anymore. It started from a square, which was n by n. It went over here, right? So it's now n minus 1 up and n plus 1 across. So that is equal to 2n, choose, you said n plus 1, okay? At that point, we're actually almost done. So this is actually very fast. It suffices to subtract it from 2n, choose n. So the Catalan number is equal to your 2n choose n minus the number of these things which go across and end over here instead. And that happens to be the 2n choose n plus 1. Okay? And how would you simplify that? Well, we actually know what our target is now. We know we have a formula, and the target is 2n choose n times something. So what would you do here? Well, we would probably keep the 2n choose n in front. The other thing, though, we want to express in terms of 2n choose n. Right? So we would like to have 2n factorial over an n factorial, but that's not what that is. So what do I need to multiply this by? N over n plus 1, because this n plus 1 will combine there to make an n plus 1 factorial. This guy takes out an n, so you get n minus 1 factorial. Wow! 1 minus n over n plus 1. You are done. That's the entire Catalan number formula. We didn't do any generating functions or anything else, it just came right up. Nevertheless, I wanted to show the other thing as this sort of a tour. Okay. Actually, this reflection principle is useful for other things too. Because if you're talking about the politician who never wants to be below half, you could even ask about different versions where they're willing to be below half, but they're not interested in being too below half. Okay? And I don't often think of that in terms of the politician. Oftentimes you would think of that maybe in terms of the gambler. It's like the gambler who starts with $2 and starts gambling, but you're not allowed to have a negative $2. Does that make sense? But at this point, you can ask other questions like, how many points never go below a line that's 2 below? And how would you answer that now? You do the same thing. You just do a reflection across the dotted line that's 1 more below that. So this is like a more general way of analyzing the same thing. Okay, so at that point, I guess now we're ready to roll back to the original question. And you are right. The idea of how these all are related to this very first thing I talked about is the reflection principle. You can analyze this first thing by reflecting. Let me go back over here. But reflecting over what? And it's not really reflecting either. It's different. So this very first question that I opened with said that here we have 2 points, an A and an A prime. And we have over here a B and a B prime. Is this what we had before? And before, what we were trying to prove is we were trying to show that if you take the number of paths going from A to B, multiplied by the number of paths going from A prime to B prime, that this was always less than, no, yes, that this was always less than the number of paths that go from A to B prime times the number of paths that go from B to A prime, no, A prime to B. Does this make sense? That's what we had before. Well, now we know that we can do stuff about reflections. And when we're doing a counting thing, the number on the left is actually counting something. We're multiplying two things. So we're counting the number of pairs of paths. Does that make sense? So the thing on the left is the number of pairs of paths, where we have a path going from A to B, and a path going from A prime to B prime. And what does that pair of paths look like? Well, it looks like something like this. So here's the A going to the B. And you also have another path, which is going from, say, the A to the B prime. So this is one pair of what we're counting. In general, whenever you're trying to prove a combinatorial result and you think you might want to do it by counting, you want to identify on the left-hand side what you're counting, and that's now ordered pairs. And once you think about ordered pairs, then you want to start to compare these ordered pairs to the ordered pairs on the right. Okay? Because now we're not dealing with one path that we're reflecting stuff about. We always have two paths to play with at the same time. And over here on the right, this is the number of pairs of paths which go from A to B prime and from A prime to B. And now here's the question. How can you turn a path on the left-hand side into one of the paths on the right-hand side? Sorry, one pair of paths on the left into the pair of paths on the right? Well, there's a reflection idea. Well, yeah.
You reflect over their point of intersection.
Well, if you reflect over their point of intersection, they end at different places. Do you know what I mean? It's not exactly a reflection, but
You just like take the beginning of one and swap it with the end of the other, or the beginning piece of the end piece. Right.
you change them. You reroute them at the point of first contact. This is awesome. This is actually really slick. This is awesome. No, remember, otherwise you're dealing with 8 variables and multiplying binomial coefficients with factorials. You can't do that nicely. But what we're saying here is if I have this pair of paths, well, at the moment of their very first intersection, it's switch their tracks. Okay? So what we do here is for each of these, switch tracks at first hit. And that will immediately give you the ones that go the other way. Well, we've got to double check a few things. The first is that they will intersect. But they will. That's the intermediate value property again. Does that make sense? That's actually why I wanted this one to be out here, and this one to be up there, and then this B to be down here, B prime down here, B over there. So they will actually always intersect. Always exists. And it's also clear that you can figure out how to go from one of the other ones back simply by saying, well, no, that's actually not true. I don't want a bijection. I don't know how I can always go from one of them back. What I want is an injection. So what I want to say is, if there is one of these paths like this, there's only one way to do it. But there is. You just go to the first spot and switch back. And then why then is it less? Well, it's less.
You just showed that there's one thing on the left that doesn't, on the right that doesn't.
Yeah. And what do those look like?
Just like that.
Just like this and this.
Yeah.
Right? So this is a beautiful question. I mean, basically what this is explaining is that the ones that go longwise always will cross, and therefore you can switch tracks.
Wait, can you restate the original problem?
Oh, yeah, because yeah, absolutely. The original question was actually this. The original question is whenever you have 2 points where the A is to the left, here are the quadrants, right? So if you have A and A prime in this quadrant, oriented like so, and if you have B and B prime in the bottom right quadrant, oriented like so, then if you count the number of paths from the A to the B and multiply that by the number of paths from the A prime to the B prime, you'll get a number. We actually numerically did this a few times. And that number was always less than the number of paths from the A prime to the B times the number of paths from the A to the B prime. And so this was an observation that we just made during the warm-up that seems to always work.
But like, number of paths from like A to B and A prime to B prime, like they don't necessarily have to intersect because you could have one.
A prime to B prime go like this, and
Oh.
then A to B go like outside.
So these are like shortest paths.
Oh.
So the important thing is that these are shortest
Oh,
paths.
okay, yeah.
Oh yeah, I should have been clear because otherwise the answer is there are infinitely many paths.
Yeah.
Right. So these are the shortest paths which are only allowed to go east and south.
Okay.
Yes. And so that's what we opened with. We opened with this warm up, just counting how many, discovering that there was this nice pattern, and the relationship between all the problems is that, of course, these aren't Catalan numbers, but this is showing you that you can use these reflection type ideas to prove very, very nice statements very elegantly. So yeah, so that's actually where I wanted to finish for today, and yeah, thanks very much. So we're done. Do you want to, if you have any questions or random stuff you want to chat about, totally happy to do that. Yeah.
I just have like, so when you multiply those two, like, could that also be like if you were to shift like A prime, B prime, that kind of like half, so that B prime was on A?
So B prime was on A.
Yeah, and then it will be like a bigger rectangle.
Yeah.
And the product will be like the number of paths that go through A.
Right.
And then like you would also look at the other rectangle where you shift A prime B onto A B prime. I don't know how to like compare them somehow.
So I'm afraid I don't completely understand your question. I don't completely understand your question. What I'll say is that if your paths can still be retracked, this argument will still work. If your paths cannot be retracked, it could be very complicated to try to prove because it would involve binomial coefficients that have many, many variables involved. Yeah. Any other questions?
So,
Yeah.
well, what is XP like? I actually have never been inside that.
Oh, that wasn't actually what I came to talk about. But what is XP like is that we were sponsoring Armo, but that's actually why all these shirts are up. But in a nutshell, we're creating the interactive Wikipedia so that everyone in the world can learn from free interactive lessons. And when I say interactive, I mean something that's not just a video for 5 minutes or not just like a page of text, but where you have some mix between some hopefully engaging video, which is really short, and then some questions that you're always thinking about every few seconds. So the idea is that if you were going to tutor someone, actually do you tutor people or no? Sometimes. Yeah, and like if you're a really good tutor, what you'll do is you won't just talk at them. You'll sort of ask questions every so often to make sure they're following, and you will even have a script in your head of like if they answer one way, what would you do? But in some sense, this is a problem that thousands of people are solving simultaneously every day. And what we're doing is we're crowdsourcing and recording this sequence of questions that you would ask if you were tutoring on a subject. And the idea is that you can even put on video to help make it more engaging, perhaps. And our idea is that actually crowdsourcing this script is not, in fact, that hard. And if we had all these scripts recorded, then everyone in the world would essentially have the experience of talking to a tutor for free. Just like how Wikipedia recorded the scripts called reference materials, right? But they're non-interactive scripts. So that's what XP is about. We're trying to improve scientific and mathematical literacy worldwide.
How is XP funded?
So it's actually a startup company. So the
You
idea.
didn't like give that pitch to some venture capitalist.
So we already did. So in fact, one of the biggest investors is the person who was the first chief technology officer of Facebook, and he also runs a company called Quora. We also, I'm also in New York because I'm meeting with one of our venture capital firms here tomorrow. It's called Great Oaks Venture Capital. And so the idea is, actually when I originally started the whole thing, I was even thinking of maybe doing it as a nonprofit. Because as you heard, the ultimate objective is to improve scientific literacy and improve mankind. But
They want to make money.
what's that?
Well, venture capitals.
They do. But at the same time, if you think about it, in some sense, the world is built from companies that do stuff, right? And in another sense, I guess when I was thinking about it, ultimately what swayed the needle was I saw that if you were a nonprofit, you would always need to be asking for donations in order to even survive for the next year. That's overgeneralization. That's not completely true. But you would still need to worry about those sorts of things. And we realized that actually this is a large sector of the economy called education. There are some things in it where not everyone will want to buy. For example, what I just described as this free reference is very cheap for us to run. because we are crowdsourcing the content and then delivering it. However, there are other things that some people might want. For example, private tuition, or if they want to have tutoring, right? Then there are these other services which you can offer onto the side. So ultimately, the idea is, if you actually are in a space where there are people paying for certain educational services anyway, then if you have actually built a platform that has scaled to 10 million, 100 million
Kind of
people.
like how AOPS does it. They have, their classrooms.
Right.
They also have AOPS Wiki and everything.
Right. So actually, that's a really good analogy. Like with art of problem solving, which you're just mentioning, the idea is that it's crowd created, and the crowd created part is free. But some fraction of the crowd wants additional services, which then create revenue that finance the whole free operation for the good of everyone else. So in this case, it happens that we are a little bit different from AOPS in that our goal is, our target audience is actually the whole, like the big 95%, not just the top 5%, if that makes sense. I think that AOPS does a fantastic job of providing a great service for the top 5%, and one needs that. But we actually want to make more people interested in math and science, period. And that's partly influenced because I'm coaching the IMO team. And I realized that if we want to do better, we can't only teach the top people, because there aren't enough of them. We also need to juice up the pipeline and just get way more people in America or worldwide just interested in math and science. So yeah, so it actually makes money. Well, it doesn't. It loses a lot of money right now. But something. It's like all the other big startups that eventually became mass consumer plays, right? Is that some fraction of people will pay for Gmail. I mean, how many of you pay for Gmail?
You pay for Gmail?
Yeah, we do. Because no, well, that too. But universities pay and companies pay. So for example, XP is a company. We need to pay for Gmail because we want to have their additional services. And so the idea is that everyone's free Gmail is paid for by a small fraction which wants to pay anyway for something. Does that make sense? So with XP, the idea was to realize, oh, wait a second, if we become a for-profit in a naturally monetizable space, you can provide that service at a high level of quality like Gmail, right? But at the same time, the income that you get can actually offset all costs. And in fact, at the end of the day, you can even sponsor math contests. And you can donate to nonprofits. And you can basically support the nonprofit sector, which you would otherwise be competing with for donations. So that's why we went that way. But yes, that's the idea. I mean, basically, I thought of this thing when I was trying to find a way to get more people into math and science. And I decided that given that not everyone has access, maybe to the schools that you guys are attending, in some sense, if everyone who has gone through these schools is recording the exchanges of how they learned it, how it makes sense to them, then no matter where you are in the world, whether you have access to Stuyvesant or not, or any of the other schools that you're attending, then you'll have an approximation of that experience. That's what we do. And we like to sponsor math contests because we're built by the enthusiast community. I mean, that's, in some sense, I'm from the enthusiast community from years ago, and I guess the thought was, I think the enthusiasts can actually build a very, very, very good website, which actually has ways of communicating why we are interested enough about math and science to be spending Sunday doing math. Did that answer your question?
Yeah.
Okay.